Hi, I'm Alex. Out there in the universe are worlds nothing like Earth, planets of fire, darkness, and crushing extremes where survival seems impossible. Some melt, some freeze, some swallow, all light, and some may still hide life in ways we've never imagined. In this journey, we explore the most deadly alien worlds ever discovered and what they reveal about life survival and how fragile our own planet truly is. If journeys like this spark your curiosity, a gentle subscribe helps this journey keep growing and quietly offering more. Now let's begin. The universe, vast and indifferent, once seemed empty to us. Before March the 7th, 2009, we gazed into the darkness with instruments that could barely scratch the surface of what lay beyond our solar system. We wondered, we doubted, we felt the crushing weight of cosmic loneliness pressing against our collective consciousness. Then came Kepler, and everything changed. Kepler was not just another telescope pointed at the stars. It was a massive light-measuring machine, a sentinel designed to stare unblinking at a single patch of sky for nearly a decade. Imagine standing guard at a cosmic gateway, watching, waiting, never looking away, never missing a single flicker of light across 150,000 stars simultaneously. That was Kepler's mission, its purpose, its obsession. The method behind this mechanical guardian was both elegant and brutally precise. When a planet passes in front of its parent star, from our perspective, it blocks a tiny fraction of that star's light, sometimes as little as 0.01%, a dimming so subtle it would be invisible to human eyes. To put this in perspective, that might resonate with your daily experience. Detecting this change is equivalent to spotting an ant crawling across a car's headlights from a distance of 100 meters in the darkness, while that car speeds down a highway, like the first time you peer into a microscope and realize an entire living world exists in a single drop of water. Kepler revealed that we had been staring at an ocean teeming with worlds we simply couldn't see. Every 0.01% dip in starlight meant a new world emerging from the darkness, announcing its existence through the shadow it cast. One by one, hundreds became thousands. The data flooded in like a revelation, each light curve telling the story of a planet we never knew existed. Rocky worlds, gas giants, super Earths, worlds so strange they defied our categories and forced us to create new ones. By the time Kepler's mission concluded, it had confirmed more than 2,600 planets orbiting distant stars. But the numbers tell only part of the story. What Kepler truly proved shattered our assumptions about our place in the cosmos. Small rocky Earth-like planets were not rare cosmic accidents, not precious anomalies scattered across an otherwise barren universe. They were the rule, not the exception. The galaxy was not empty. It was crowded. Before Kepler, we were alone in our ignorance, suspended in doubt. After Kepler, we knew with statistical certainty that billions of worlds existed beyond our reach, each one a unique story waiting to be read. And here's the staggering truth that should make you pause. Those 2,600 confirmed planets are merely the tip of an incomprehensibly massive iceberg. The Milky Way galaxy likely harbors between 100 and 400 billion planets. Billion, with a B. Kepler watched one tiny corner of the sky, a cosmic keyhole view representing just 0.25% of the entire celestial sphere. Imagine what lies in the 99.75% we haven't surveyed with such intensity. The implications are dizzying, overwhelming, humbling beyond measure. but Kepler only found them catalogued. Their existence proved they were there in numbers that strain comprehension. That was merely the first step in a much longer journey. Now, we needed to know something more fundamental, more urgent, more deeply connected to our own survival and purpose in this vast cosmos. We needed to know what they actually were. On April 18th, 2018, humanity launched a different kind of hunter into the void. The transiting exoplanet survey satellite TESS carried with it a revolutionary philosophy that would reshape our search for other worlds. Where Kepler stared deep into one distant patch of cosmic real estate, TESS would take a fundamentally different approach. Don't look far. Look close. Look carefully. TESS doesn't aim its instruments at the farthest reaches of the galaxy, seeking worlds thousands of light years away that we could never hope to study in detail. Instead, it focuses on nearby bright stars, the stellar neighbors, within just 200 light years of Earth. These are stars close enough and bright enough that ground-based telescopes can follow up powerful observatories that can do something Kepler never could analyze. The atmospheres of the planets TESS discovers, searching for the chemical fingerprints of life itself, the biosignatures that would prove we are not alone. If Kepler was a solitary astronomer peering through darkness at distant shores, TESS is the neighborhood detective, methodically mapping every street, every house, every corner within reach. The strategy is brilliantly practical. TESS surveys an astonishing 85% of the entire sky, constructing a grand mosaic like assembling pieces of the largest puzzle humanity has ever attempted. It divides the celestial sphere into segments, observing each one for 27 days. Before moving to the next building, a comprehensive catalog of worlds orbiting the stars we can actually reach with our current and near future technology. The mission has already transformed our cosmic senses. As of now, TESS has confirmed over 390 exoplanets and created a list of more than 6,600 potential candidates awaiting verification. Among these discoveries lies one of the most significant finds in astronomical history: the TRAPPIST-1 system, 7 Earth-sized planets orbiting a cool red dwarf star, several residing in the habitable zone, where liquid water could potentially exist. But why limit the survey to 85%? What about the missing 15%? The answer reveals the practical realities of space exploration. That remaining fraction of sky is temporarily blocked by the sun and moon from TESS's orbital vantage point, cosmic blind spots that shift over time but prevent complete coverage during any single observing cycle. Like when you've lost your keys and the old wisdom applies, don't search the entire city in a panic check around your house first. Look in the places you can actually reach. Kepler gazed far like a lonely astronomer, dreaming of the distant shores. TESS sweeps horizontally like the security camera system of the entire galaxy, watching our neighborhood with meticulous attention. The fundamental goal driving TESS goes beyond mere planet detection. Every nearby bright star with a transiting planet becomes a target for atmospheric analysis by the next generation of observatories. The James Webb Space Telescope, ground-based giants, and future missions will point their instruments at these worlds, splitting their light into component wavelengths, searching for oxygen, methane water vapor, the chemical signs that life may have taken root somewhere beyond Earth. This is the ultimate prize. the answer to the question that has haunted humanity since we first looked up at the night sky and wondered, are we alone? With these new weapons in our arsenal, we began penetrating the mysteries of the closest worlds to our own solar system. We expected to find planets, variations on themes we already knew, perhaps some surprises that would expand our understanding of planetary formation and evolution. What we actually discovered surpassed our worst nightmares and challenged everything we thought we knew about the limits of physical reality. This is where the story shifts from pure science into something far darker, something that challenges not just our understanding of planetary physics, but our assumptions about what is possible in this universe. Located approximately 750 light years away from Earth, discovered in 2006 by the Transatlantic Exoplanet Survey, TRES-2b, stands as one of the most profoundly unsettling worlds humanity has ever detected. It is unlike any planet we have ever known, not by emitting light, not by reflecting it in brilliant displays of atmospheric glory, but by swallowing it whole, consuming photons like a cosmic predator that feeds on illumination itself. TAR-ES-2b absorbs more than 99% of the light that strikes its surface from its parent star. Let that sink in for a moment. This world is darker than coal, darker than the blackest charcoal ever produced in human furnaces, darker than any synthetic material our scientists have engineered in laboratories, specifically designed to create light-absorbing substances. It is quite literally the darkest known planet in the observable universe, a sphere of near absolute blackness drifting through the void like a hole torn in the fabric of space itself. Scientists call it the darkest known planet, but more important questions haunt those who study this mysterious world. Why is it so dark? What is happening in its atmosphere to create this unprecedented light absorption? The leading hypothesis points to gaseous titanium oxide molecules saturating the planet's atmosphere compounds that can absorb light with the efficiency of military-grade camouflage, paint drinking, in photons across multiple wavelengths. But here's the optical paradox that makes TAR-ES-2b so deeply strange. This planet is tidally locked to its star, orbiting so close that its day side reaches a searing 1,000 degrees Celsius. At such temperatures, objects should glow red hot, emitting their own thermal radiation in visible wavelengths. Yet, TAR-ES-2b remains dark, a smoldering ember floating in eternal night, twice the size of Jupiter, yet nearly invisible against the cosmic backdrop. Some astronomers willing to venture into more speculative territory have proposed bolder hypotheses. Could this represent some form of optical concealment, technology created by a super advanced civilization, a planet-scale invisibility cloak that defies our understanding of physics? The idea sounds like science fiction, yet the reality of TAR-ES-2b's darkness demands explanations that stretch conventional theories to their breaking point. The implications are chilling. Imagine such an object, a colossal, completely black sphere, twice Jupiter's size, drifting through space, reflecting virtually nothing existing, as though it were not there at all. If TAR-ES-2b somehow broke free from its star and drifted into our solar system, we might not detect it until its gravitational influence began tearing our world apart. We wouldn't see it coming. No reflection, no warning, just a massive, invisible threat approaching through the darkness. The potential military applications of understanding this absolute light absorption have not gone unnoticed by those who think about such things. Materials that could absorb light across all wavelengths would revolutionize stealth technology, creating surfaces that could render objects truly invisible to optical and infrared detection systems. You might be able to imagine driving into a tunnel, a reasonably long tunnel, perhaps a few kilometers through a mountain. Now imagine that tunnel stretches for 12,000 kilometers in absolute perfect darkness, no lights, no reflections, nothing but void pressing against your consciousness. TAR-ES 2b is an entire planet, like that a world-sized tunnel into blackness from which light never escapes, yet as terrifying as eternal darkness might be as unsettling as a planet that swallows light. TRIS 2b represents only the beginning of the horrors we have discovered among the exoplanets. Darkness, it turns out, is not the worst fate a world can suffer. There are places where the sky rains molten stone. If TAR-ES 2b showed us a world that devours light, these twin nightmare planets reveal something even more viscerally terrifying worlds, where the very concept of solid ground becomes meaningless, where the fundamental states of matter we take for granted dissolve into chaos, where hell itself seems like a reasonable description. CoRoT 7b lurks 489 light-years from Earth in the constellation Monosros, discovered in 2009 by the French-led CoRoT mission. This super-Earth measures approximately 1.5 times our planet's diameter, but any similarity to our homeworld ends there. It orbits its parent star at such an impossibly close distance that a complete year passes in less than 20 hours. 20 hours. A day on Earth is longer than an entire year on CoRoT 7b. Due to tidal locking, one hemisphere, eternally, faces the star, creating a hellscape where surface temperatures reach 2,600 degrees Celsius, hot enough to melt and vaporize rock. The night side, forever turned away from its sun, freezes solid like steel. The temperature differential between these hemispheres spans thousands of degrees, generating supersonic winds that scream across the planet's surface, carrying clouds of pulverized rock dust. But here's where CoRoT 7b transcends normal definitions of hostile environments. Its atmosphere contains no water vapor, no breathable air, no familiar gases at all. Instead, the atmosphere consists of rock vapor, literally rocks that have evaporated into gaseous form, rising from the molten surface. These vapors cool. As they rise, condense at altitude and fall back down as rain. Not water rain, not even acid rain, rock rain, molten granite droplets falling from clouds made of vaporized stone. Weather forecast for today: extensive granite clouds, high probability of lava precipitation, high temperature sufficient to vaporize your soul. K2-141b takes this concept of geological horror and amplifies it to incomprehensible extremes. Nearly the entire surface of this planet lies submerged beneath a vast ocean of molten lava, extending hundreds of kilometers deep, a magma sea that makes Earth's volcanic activity look like a child's science experiment. The atmosphere consists of rock vapor, primarily sodium and silicon oxide gases that rise from the superheated magma ocean. These gases cool at altitude, condense, and fall back as a relentless rain of molten metal and liquefied stone splashing into the lava sea below. The planet operates on a hydrological cycle, but instead of water evaporating from oceans to form clouds that produce rain, K2-141b features rock evaporating from magma oceans to form vapor that produces molten stone precipitation. Scientists studying this world have identified circulation patterns in the magma ocean resembling Earth's ocean currents, great rivers of molten silicate flowing through the lava driven by temperature gradients and the planet's rotation. Magma waves rise and fall like swells on a terrestrial sea, except these waves consist of material hot enough to instantly vaporize any known spacecraft material. The planet continuously erodes and recreates itself in this brutal cycle, surface material vaporizing into the atmosphere, condensing, falling back, melting into the magma, ocean circulating through convection currents, rising to the surface again, an endless process of destruction and reformation playing out across geological time scales, compressed into everyday planetary weather patterns. Every time you complain about a 40-degree-Celsius summer day, remember there are worlds where you would vaporize before your body hit the ground. Both planets share one absolute characteristic. No safe zones exist, no shelters, no places to hide from the relentless heat. These are worlds where the concept of survival becomes meaningless, where life as we know it could not exist for even a fraction of a second. Yet as horrifying as raining molten rock might be, the universe has reserved even more creative methods of planetary destruction. There are worlds where the rain doesn't fall down at all, but flies horizontally at speeds that defy comprehension. HD 18973b appears deceptively beautiful. From a distance, its atmosphere scattering light to create a striking azure blue color reminiscent of Earth's life-giving oceans. This visual deception makes it one of the cruelest jokes the universe has ever played on humanity's search for habitable worlds. Beneath that gorgeous blue exterior lies a hell more violent than anything we encountered on Korot 7b or K2-141b. The winds on HD 1897333b reach speeds of 8,700 kilometers per hour, fast enough to circumnavigate Earth's equator in just a few hours, velocities several times the speed of sound, screaming through an atmosphere laden with silicate particles. These aren't gentle breezes carrying water droplets. This is a planetary-scale shredder operating at supersonic velocities, and the precipitation makes the nightmare complete. The silicate compounds in the atmosphere condense at altitude into molten glass droplets, but these glass rain droplets don't fall straight down as rain does on Earth. The supersonic winds catch them, accelerate them, turn them into horizontal projectiles, traveling at speeds that would put military weaponry to shame. Each microscopic glass particle becomes a bullet, millions upon millions of them, screaming sideways through the atmosphere in an endless barrage. The entire atmosphere functions as a colossal grinding machine, pulverizing anything that could possibly exist there into component atoms. What keeps such a dense, silicate-laden atmosphere moving at speeds far beyond any aerodynamic limits? We understand. The question haunts atmospheric scientists who study this world. The energy required to maintain these wind speeds defies conventional models of planetary circulation. Then we encounter 55 Cancri E, the so-called diamond planet, and here the universe reveals its darkest sense of irony. This world possesses an abnormally high carbon content, leading to conditions where carbon compounds don't just exist, but dominate the planetary composition in ways that sound like pure fantasy. 55. Cancri E is a tidally locked super-Earth, where the daytime hemisphere reaches temperatures high enough to melt most metals and silicate materials, creating a liquid magma crust that flows like a burning river across half the planet. Meanwhile, the night side still maintains a staggering 1300 degrees Celsius, hot enough to melt aluminum, but cold enough relative to the day side that carbon vapors can condense and crystallize. Beneath the surface, crust may lie an ocean of liquid diamond pressures and temperatures combining to create a state of carbon that exists nowhere on Earth. This is the only planet in the known universe where being fantastically wealthy wouldn't save you. You've dreamed of winning the lottery, perhaps imagining what you'd do with unimaginable riches. Now imagine winning an entire planet made of diamond and realizing you can never reach it, never touch it, never benefit from wealth measured in quadrillions because the surface temperature would vaporize you in milliseconds. But perhaps the most existentially disturbing world among this trinity of apocalypse is WASP 12b, a hot Jupiter spiraling toward its doom in a cosmic death spiral we can observe in real time. This planet orbits its parent star at such a brutally close distance that tidal forces have stretched it into an egg shape, no longer spherical, but grotesquely distorted by gravitational stress. WASP 12b is bleeding. Every second streams of planetary material flow from the planet into its star matter, torn away by tidal forces and stellar winds. Based on measurable rates of mass loss, astronomers have calculated a horrifying timeline. WASP 12b will be completely consumed by its parent star in just a few million years. We are watching a planet commit slow suicide, or perhaps more accurately, watching a star murder its own planetary child, while we stand as helpless witnesses across the void. These three worlds prove something fundamental about the universe we inhabit. Nature has infinite methods for destroying planets, endless creative ways to render worlds uninhabitable, countless paths to oblivion, glass bullets flying at supersonic speeds, wealth beyond imagination that remains forever untouchable, slow consumption by the very star that gave you life. This is where the first act of our story reaches its darkest point. We've witnessed the hunters that found these worlds. We've seen darkness that swallows light, rock rain, and magma oceans. And now this trinity of apocalyptic destruction. After witnessing hell in so many forms, does any hope remain? Could anything exist beyond this catalog of horrors? It turns out the universe contains things stranger than hell itself. Hidden within the Centaurus constellation, approximately 434 light-years from us, lies a planet, or perhaps an unimaginably massive object called J1477b. It was first detected in 2007 and analyzed further in 2012, when astronomers realized it was causing a series of strange dimming events in the star V1400 Centauri eclipses, unlike anything witnessed before in the history of planetary science. With an estimated mass between 10 and 40 times that of Jupiter, J1407b occupies an uncertain territory in cosmic classification. It could be a supermassive planet, or it might be a brown dwarf, a failed star that never accumulated quite enough mass to ignite nuclear fusion in its core, forever trapped in the liminal space between planet and star, neither one thing nor another. But mass alone doesn't make J1407b extraordinary. What truly elevates this world into the realm of the magnificent, what transforms it from mere astronomical curiosity into a symbol of cosmic grandeur is its ring system. More than 30 rings, spanning nearly 120 million kilometers in diameter, a structure so monumentally vast it defies human comprehension. These rings are approximately 200 times larger than Saturn's famous ring system, the structure we consider the crown jewel of our solar system, the most beautiful planetary feature humanity has ever observed from Earth. Saturn might proudly declare, "I have the most beautiful rings in the solar system," to which J1407b would calmly respond, "Hold my beer." Each ring could contain an amount of material equivalent to hundreds of moons enough mass to construct entire planetary systems. If J1407b somehow replaced Saturn in our solar system, its rings would cover nearly the entire visible sky of Earth, from horizon to horizon, resembling the wings of an ancient god stretched across the heavens, a sight so overwhelming it would fundamentally alter human culture, religion, and our conception of our place in the universe. Imagine looking up at the sky and seeing luminous bands arcing from one horizon to the other day and night, dominating every view, every photograph, every moment of existence. That would be the reality from any moon orbiting within J1407b's system. Scientists studying this colossal ring structure have identified gaps between the ring spaces where material has been cleared away. These gaps raise fascinating questions about what's happening within this system. Are they evidence of moons currently forming, sweeping up material in their orbital paths? Or are they remnants of something far more violent, the aftermath of a catastrophic collision where an Earth or Mars-sized moon shattered into billions of fragments of rock and ice scattered across millions of kilometers? We may be witnessing a fleeting moment in cosmic time, observing either the birth pangs of a new moon system or watching the slow death of ancient structures that existed long before humanity evolved. These rings may be temporary by cosmic standards, perhaps destined to disappear within a few million years as the material either coalesces into moons or disperses into space. The existence of J1407b forces us to confront uncomfortable questions about scale and permanence. This magnificent ring system, larger than anything in our solar system, visible across interstellar distances, may represent only a brief moment in the eternal flow of cosmic time. Like a spectacular sunset that fades within minutes, J1407b's rings might be a transient phenomenon we're privileged to observe during this narrow window of human civilization. But these rings had to come from somewhere, had to form through some process of creation or destruction. Where does such a massive structure originate? What cosmic violence or patient accumulation creates rings that dwarf anything we know? The answer lies in death itself, in the violent endings of stars. At this point in our journey, the story transforms into something that transcends simple categories of living or dead worlds. We enter the realm of planets that cannot be killed, worlds that have survived conditions so extreme they should not exist, yet they persist. They endure, they testify to a resilience that challenges everything we thought we knew about planetary survival. PSR 1257 plus Topum B holds the distinction of being the first exoplanet humanity ever discovered detected even before we found planets orbiting normal living stars. This planet doesn't orbit a star in any conventional sense. It orbits PSR 1257 plus 12, a pulsar, the rapidly spinning core of a star that has already died, collapsed, and been reborn as something alien and hostile to everything we understand about life-supporting environments. A pulsar is a stellar corpse that spins at incomprehensible velocities, in this case, rotating 161 times per second, emitting powerful beams of electromagnetic radiation and gamma rays, like a cosmic lighthouse broadcasting death across the void. These radiation beams don't illuminate in any gentle sense. They tear through matter at the molecular level, breaking apart complex structures, destroying chemical bonds, rendering organic chemistry impossible. Yet PSR 1257 plus 12b exists in this hellscape of radiation. The fundamental question haunts every scientist who studies this world. Why can matter withstand this level of molecular decomposition? What composition could possibly survive in the intense radiation field surrounding a pulsar? The answer reveals something profound about planetary formation. PSR 1257 plus 12b is a second-generation planet born after the death of its parent star from the debris of the supernova explosion itself, like a phoenix emerging from cosmic ashes. The material that forms this planet was forged in the most violent event in stellar evolution, compressed, transformed, and scattered, before gradually coalescing again into planetary form around the remnant core. V391 Pegasi b tells an equally impossible story of survival. This planet orbits a white dwarf, a star that has exhausted its nuclear fuel and collapsed into a dense stellar remnant. But the remarkable aspect of V391 Pegasi b isn't where it is now, but where it was before what it survived to reach its current orbital position. When its parent star expanded into a red giant phase, it began swallowing the inner planets of its system. V391 Pegasi b was within range of this catastrophic expansion. The planet was literally inside a dying star, engulfed by stellar material at temperatures reaching thousands of degrees Celsius. Through mechanisms we still don't fully understand, V391 Pegasi b survived being cooked within a cosmic crematorium. The outer gas layers of the planet likely boiled away into space, stripped by stellar winds and intense heat. But the rocky core endured. It survived immersion in its own star temperatures that should have vaporized it, radiation that should have torn it apart, and emerged on the other side intact, enough to continue orbiting in a stable configuration. Like survivors of catastrophic disasters who carry their stories with them, forever changed, these planets bear witness to resilience that seems impossible, endurance beyond reason. The lesson they teach us is simple but profound. Some worlds cannot be killed. They survive stellar death. They endure pulsar radiation. They persist through being swallowed by their own parent stars. Against all odds, against everything physics suggests should destroy them, they remain. We have seen hell in its many forms, witnessed wonders that dwarf our solar system's greatest features, and now observed immortality in worlds that refuse to die. But what truly makes us human, what drives our exploration across these impossible distances, isn't curiosity about destruction or even wonder at cosmic magnificence. What we truly crave is hope. After witnessing the cosmic horrors and immortal worlds that defy death itself, we arrive at the concept that drives humanity's search for life beyond Earth, the habitable zone often called the Goldilocks zone, that narrow band of orbital distance where conditions are not too hot, not too cold, but just right for liquid water to persist on a planetary surface. But here's the uncomfortable truth, revealed by decades of exoplanet research. The Goldilocks zone is not a simple ring around a star where we can expect to find Earth-like paradises waiting for human colonization. It's a complex, multifaceted region dependent on stellar-type planetary atmosphere, geological activity, magnetic fields, and countless other variables we're only beginning to understand. Most Earth-sized planets discovered by our missions orbit red dwarf stars, specifically M-type stars, the quiet giants that account for approximately 75% of all stars in our galaxy. These dim, cool stars burn their nuclear fuel so slowly they could theoretically shine for trillions of years, far longer than the current age of the universe itself. Their longevity makes them attractive candidates for hosting life, offering stable environments across geological timescales that dwarf the lifetime of stars like our Sun. But red dwarfs present a cruel paradox. Because they burn cooler and dimmer than Sun-like stars, their habitable zones lie much closer to the star, pushing potentially life-bearing planets into orbits tighter than Mercury's path around our Sun. Due to these tight orbits, planets in red dwarf habitable zones are almost certainly tidally locked with one hemisphere perpetually facing the star in eternal daylight, while the other remains trapped in endless night. Goldilocks might have said, "Not too hot, not too cold, just right." Red dwarf stars respond, "I'll decide what temperature is right. Thank you very much." The situation grows more challenging when we consider stellar behavior. In their early stages of life, red dwarfs often flare up dramatically, sending out X-ray and ultraviolet radiation storms that can be 100 to 1,000 times more powerful than anything our Sun produces. This high-energy radiation doesn't just warm planets. It strips away atmospheres through a process called hydrodynamic escape, tearing molecules apart with such force that light elements like hydrogen are blown into space. This radiation breaks down water molecules into hydrogen and oxygen, then ejects them beyond the planet's gravitational hold. Within just a few million years, a potentially habitable world can be transformed into a desiccated, airless rock resembling Mars, all traces of water vapor and protective atmosphere scattered into the cosmic void. It's like finding the perfect seat beside a campfire, close enough to feel warmth, but far enough to avoid burns. The universe works on the same principle, except the fire occasionally explodes with 1,000 times its normal intensity. Even if a planet survives this early stellar violence and manages to retain or rebuild a secondary atmosphere composed of heavier gases like carbon dioxide and water vapor, the challenges don't end. The planet must maintain this atmosphere against ongoing stellar activity, must develop some form of magnetic field to deflect charged particles, must possess the right geology to recycle atmospheric gases over millions of years. Yet despite these obstacles, despite the countless ways the universe can sterilize potentially habitable worlds, somewhere among the billions of planets in our galaxy, candidates exist that might beat the odds. Among these billions of worlds, 2 candidates stand out as particularly promising, 2 planets that could perhaps become humanity's second home. TOI 700D emerged from the data streams of TESS in January 2020, a discovery that sent ripples of cautious optimism through the astronomical community. Located approximately 102 light years away, this planet orbits a quiet red dwarf star, and that single word quiet carries more significance than you might initially realize. It represents the deciding factor between a sterile rock and potential cradle of life. The planet measures roughly 1.19 times Earth's radius, placing it firmly in the super-Earth category, but close enough to our own world's dimensions that comparisons feel meaningful rather than absurd. It completes an orbit every 37.4 days, receiving about 86% of the energy Earth receives from our Sun, a number tantalizingly close to the sweet spot we know can support liquid water. Early climate models have painted three possible scenarios for TOI 700D's atmospheric conditions. The first envisions a thin Mars-like atmosphere that would cover the planet in ice, a frozen wasteland where water exists only in solid form, locked away in polar caps and subsurface deposits. The second scenario proposes an Earth-like atmosphere with potentially frozen oceans, a world teetering on the edge of habitability. But the third scenario, the one that keeps scientists awake at night with excitement, suggests a dense carbon dioxide atmosphere, creating enough greenhouse warming to raise surface temperatures above 0 degrees Celsius, allowing liquid oceans to exist despite the planet's tidally locked nature. If this third scenario proves true, TOI 700D might be a warm ocean world, a planetary sea heated by atmospheric blankets of carbon gases, even though one hemisphere eternally faces its star while the other remains in darkness. This makes it a prime candidate for atmospheric analysis by the James Webb Space Telescope and future observatories' instruments, powerful enough to detect biosignatures, the chemical fingerprints that would prove life exists beyond Earth. The quietness of TOI 700D's host star cannot be overstated as the critical variable in this planet's potential habitability. Unlike the violent flare-prone red dwarfs that strip atmospheres from their planets through radiation storms, TOI 700D's parent star burns with calm stability, dramatically reducing the threat of destructive stellar outbursts. This stellar temperament might have allowed the planet to retain whatever atmosphere it formed, with or to slowly rebuild after early losses, creating the conditions necessary for life to establish and persist. Meanwhile, Teegarden B orbits the ultra-cool red dwarf Teegarden's star, only 12.5 light-years away, close enough in cosmic terms to qualify as a next-door neighbor. This planet holds the highest Earth similarity index ever calculated, approximately 0.95 on a scale where 1.0 represents perfect Earth equivalence. The ESI represents a complex measure incorporating radius, density, escape velocity, and equilibrium temperature, and Teegarden B matches Earth across virtually all these parameters with uncanny precision. The planet completes its orbit in just 4.9 days, an incredibly short year. That seems incompatible with habitability until you remember its star burns so cool and dim that even this close orbital distance places the planet squarely in the habitable zone, with estimated surface temperatures remarkably similar to Earth's moderate climate zones. But Teegarden B faces the same tidal locking challenge that plagues all red dwarf planets. One side bakes in perpetual daylight, the other freezes in eternal darkness. The greatest hope for life here lies along the terminator, that narrow band between day and night where temperatures might remain relatively stable, a twilight zone where organisms could thrive in conditions that would destroy them on either extreme hemisphere. They're like two siblings facing similar hardships through different strategies. 2I-700 Turd escaped the abusive family, finding a calm parent star that doesn't lash out with radiation storms. Tea-Garden B learned to survive under harsh conditions, adapting to the narrow habitable strip its circumstances provide. Both worlds represent humanity's best current candidates for finding life beyond our solar system, each offering a slightly different path to habitability, each challenging our assumptions about where life can and cannot exist. Yet hope doesn't reside exclusively in Earth-like worlds, orbiting in comfortable zones around stable stars. Sometimes, life finds a way in the most insane places imaginable. GJ 1214b, an ocean, super-Earth, located 48 light-years away, forces us to confront the limits of our definitions. This planet orbits very close to its host star, causing surface temperatures to fluctuate between 120 and 280 degrees Celsius, a heat so intense that water in its familiar liquid form cannot possibly exist on the surface. Logic would suggest this world is hostile to life, another failed candidate in our search for habitable environments. But GJ1214b challenges the very definition of what we mean when we say life needs liquid water. Under the extreme pressures generated by the planet's thick atmosphere and substantial gravity, water doesn't simply boil away into steam. Instead, it transforms into exotic forms of ice, specifically ice vis and ice X crystalline structures that can exist at temperatures far higher than water's normal boiling point on Earth. These are ice formations that remain solid at 120 degrees Celsius, frozen but not cold, a physical paradox that seems to violate common sense. Ice Vx and Ice X represent states of water compressed into crystal lattices by pressures exceeding 10,000 atmospheres, forcing molecules into configurations that bear little resemblance to the ice cubes in your freezer. This is hot ice, a substance that shouldn't exist according to everyday experience, but emerges naturally under extreme planetary conditions. The planet's structure might resemble a sandwich of alien layers, a superheated steam atmosphere at the top, then perhaps a zone where conditions allow actual liquid water to exist, despite the high temperatures. Then beneath that, the exotic hot ice layers compressed by immense pressure, and finally the rocky core. Could life find purchase in that middle layer, that interface between steam and pressurized ice, where liquid water might persist in a thin shell around the planet? GJ1214b teaches us that the phrase life needs liquid water might be too simplistic. Life might need water, but the forms water can take under exotic conditions far exceed what we encounter on Earth's surface. Weight 5 Thief 0712 presents an even more radical challenge to our assumptions. This rogue planet wanders through space bound to no star completely isolated from external heat sources, with surface temperatures ranging from -48 to -30 degrees Celsius. It's an orphan world, likely ejected from its birth solar system by gravitational interactions during the chaotic early stages of planetary formation, cast out into the darkness to drift alone through the galaxy. How does water remain liquid on a planet that receives no light or heat from a star? The answer lies in internal energy sources that persist across billions of years. The continuous Radioactive decay of uranium, thorium, and potassium-40 in the planet's core generates steady heat, supplemented by leftover thermal energy from the planet's violent formation. These combined sources provide enough warmth to maintain a hidden liquid ocean dark, but warm beneath several kilometers of surface ice. Life on Y08550714 would not rely on photosynthesis, as Earth's biosphere does capturing solar energy to power biological processes. Instead, it would depend on chemosynthesis, drawing energy from chemical reactions at hydrothermal vents on the ocean floor, similar to the bizarre ecosystems discovered around deep-sea vents on Earth, where sunlight never penetrates. At this point in our journey, we must rewrite our definition of life itself, because life is more stubborn than we ever imagined. Life on Earth proclaims, "I need liquid water and sunlight." Life in the universe responds, "You're so weak." Like discovering a tree growing from a crack in desert rock, life always finds a way adapting to conditions we would consider impossible, thriving where we assume nothing could survive. If life can exist in hot ice, sandwiches, and on rogue planets drifting through interstellar darkness, powered only by radioactive decay, then which star system represents our greatest hope for finding not just microbial survivors, but potentially complex biospheres? In 2017, the astronomical community experienced a moment of collective shock and excitement that reverberated through research institutions worldwide. The announcement came like a thunderbolt. Astronomers had discovered not one, not two, but 7 Earth-sized planets orbiting a single, small, cool, red dwarf star just 40 light years away. The TRAPPIST-1 system had revealed itself, and with it came 7 opportunities to find life beyond our solar system. The TRAPPIST-1 star itself is unremarkable by stellar standards, a dim red dwarf, barely larger than Jupiter, cool enough that its habitable zone huddles close to the stellar surface. But what makes this system extraordinary is not the star, but its planetary family, 7 worlds, locked in tight orbits, several residing within the famed Goldilocks zone, where liquid water could theoretically persist on planetary surfaces. 7 planets means 7 chances, 7 potential cradles for life. 7 worlds where the story of biology might have unfolded, independent of Earth's evolutionary path. The odds alone make TRAPPIST-1 one of humanity's most promising targets in the search for extraterrestrial life. Yet this promising family faces a relentless challenge that threatens to sterilize every world in the system. The TRAPPIST-1 star, despite its small size and cool temperature unleashed in its youth, the kind of stellar violence that destroys atmospheres and renders planets barren. In its early life, this star produced powerful bursts of ultraviolet and X-ray radiation streams of high-energy photons so intense they didn't merely illuminate the planets, but tore through their atmospheres, molecule by molecule. This radiation doesn't gently warm planetary surfaces. It rips apart atmospheric components through a process called hydrodynamic escape, targeting light gases, like hydrogen, with particular efficiency. The radiation breaks molecular bonds, ionizes atoms, and gives them enough kinetic energy to exceed the planet's escape velocity, effectively blowing the atmosphere into space, like cosmic wind scattering leaves. Hydrogen, the fundamental building block of primordial atmospheres, becomes the first casualty in this ongoing war between star and planet. The star strips away the lightest elements, layer by layer, potentially robbing these worlds of what might have been protective shields for nascent life developing beneath. Like a family of 7 siblings living under one roof with an abusive father, these planets must learn to survive, to adapt to endure conditions that would destroy weaker worlds. But here's where the story becomes more complex and more hopeful. After the primordial hydrogen atmosphere is stripped away, a secondary atmosphere may begin to form, a denser, heavier composition made of carbon dioxide, water vapor, and other molecules more resistant to stellar radiation. These heavier gases require more energy to escape, creating the possibility that some TRAPPIST-1 planets might hold onto atmospheres thick enough to support liquid water on their surfaces. The critical question hanging over this entire system is one of resilience. Can these secondary atmospheres withstand the ongoing radiation pressure from their star? Is the rate of atmospheric loss slower than the rate of atmospheric replenishment through volcanic outgassing and other geological processes? If the answer is yes, if these planets can maintain their atmospheric shields, then they could potentially nurture life, creating biospheres that evolved under the dim red light of their parent star. If the answer is no, if the stellar radiation proves too relentless, then these worlds will end up stripped bare like Mars, their surfaces exposed and sterile, all traces of water and air scattered into the void. This is the cosmic battle playing out across the TRAPPIST-1 system, a war between stellar fury and planetary endurance, between destruction and regeneration, between death and the possibility of life. Among these 7 siblings locked in this struggle for survival, one planet stands out as potentially the strongest, the most resilient, the world most likely to have won its battle against stellar violence. TRAPPIST-1b and TRAPPIST-1c, the innermost siblings of this planetary family, have already told their tragic stories. The Hubble Space Telescope scrutinized these worlds, searching for signs of thick, hydrogen-rich atmospheres that might have survived the stellar onslaught. What Hubble found instead was failure, bare, rocky surfaces, cold and exposed beneath the faint glow of their parent star atmospheres, stripped away, leaving nothing but desolate stone. These 2 planets serve as cautionary tales, proof that proximity to even a small red dwarf can prove lethal, that the battle between star and planet doesn't always end in the planet's favor. But then we turn our attention to TRAPPIST-1 and suddenly hope flickers back to life. TRAPPIST-1 resides precisely within the habitable zone, its orbital position placing it in that narrow band where temperatures allow liquid water to exist in stable form. The planet possesses the right size, approximately Earth's dimensions, neither so small it cannot hold an atmosphere, nor so large it becomes a crushing gravity trap. Everything about its position and characteristics suggests this world might have retained or rebuilt a secondary atmosphere, rich in carbon dioxide and water vapor, creating a protective shield that could nurture life. TRAPPIST-1 is the middle child, and as any family therapist might tell you, middle children often develop the strongest survival skills, while the inner planets TRAPPIST-1b and 1c failed to maintain their atmospheres against the relentless radiation bombardment. TRAPPIST-1E's slightly more distant orbit may have provided just enough protection to allow atmospheric retention. The radiation levels remain high, certainly higher than Earth experiences from our Sun, but a thick carbon dioxide atmosphere could potentially absorb and deflect enough harmful energy to preserve surface conditions compatible with liquid water. The James Webb Space Telescope, humanity's most powerful observatory, has TRAPPIST-1E in its crosshairs. This cutting-edge instrument possesses the capability to analyze light passing through the planet's atmosphere during transits, splitting that light into component wavelengths to identify specific molecules present in the air. If James Webb detects oxygen, methane, or other biosignature gases in ratios that cannot be easily explained by geological processes alone, we will have found it. We will have discovered life beyond Earth. The implications of such a discovery would transcend science, reaching into philosophy, religion, culture, and every aspect of human civilization. The confirmation that life exists on TRAPPIST-1E would prove we are not alone, that biology is not a unique accident confined to Earth, but a cosmic phenomenon that emerges wherever conditions permit. And here's what makes TRAPPIST-1E so tantalizing. Its glows. 40 light-years away sounds incomprehensibly distant by human scales, but in astronomical terms, it's practically next door, close enough that future generations might conceivably send robotic probes to study the planet, directly close enough that radio signals from any technological civilization there would reach us within a human lifetime. Like watching 7 children grow up in adversity, we find ourselves rooting for the one with the best chance, the one who seems strongest, the one who might actually make it despite the odds stacked against survival. This discovery transcends mere scientific data. It whispers tales of resilience and adaptability of life, persisting against the harshest odds of biology, finding purchase even when physics seems determined to prevent it. TRAPPIST-1E represents our nearest hope for finding a living world beyond our solar system, a planet close enough to study in detail, positioned perfectly for habitability, potentially harboring the first extraterrestrial life humanity will ever detect. But if TRAPPIST-1 represents our closest hope for finding life, what represents our most ambitious hope? The world that most closely resembles Earth, orbiting a star most similar to our Sun, hidden among the millions of stars scattered throughout the Milky Way, approximately 1,400 light-years from Earth. In the constellation Cygnus orbits a planet that represents everything humanity has been searching for since we first wondered if other Earths exist. Kepler 452b is the reason this entire story exists, the answer to the question that has haunted us since we achieved consciousness and looked up at the night sky. Are we alone? This planet holds the distinction of being the first world ever discovered, orbiting within the habitable zone of a sun-like star. Not a red dwarf, not a pulsar, not some exotic stellar remnant, but a G-type star, a normal yellow star burning through its fuel with the same steady patience as our own sun. Kepler 452, the parent star, is older than our sun, approximately 6 billion years, compared to our sun's 4.6 billion years of age. This age difference carries profound implications. An older star means greater stability, fewer violent flares and outbursts, a more consistent energy output across billions of years. If life exists on Kepler 452b, it has had an additional 1.5 billion years to evolve beyond whatever stage Earth's biosphere has reached. Think about what an extra 1.5 billion years means. Earth's first multicellular organisms appeared roughly 600 million years ago. Modern humans have existed for perhaps 300,000 years. Technological civilization emerged only in the last few centuries. What could 1.5 billion additional years of evolution produce? Perhaps Kepler 452b hosts a civilization so ancient and advanced they would regard us as we regard bacteria. Their technology so sophisticated it would appear indistinguishable from magic to our primitive understanding. Or perhaps it hosts only ruins, the archaeological remnants of a civilization that rose and fell millions of years ago, leaving nothing but crumbling structures and unanswered questions. Kepler 452b is approximately 60% larger than Earth, with roughly twice our planet's gravity. This gravitational difference would fundamentally shape any life forms that evolved there. Height becomes a liability under doubled gravity every additional centimeter of vertical structure, requiring exponentially more energy and structural support to maintain. Life on Kepler 452b would evolve to be short, stocky, built low to the ground with thick bones and powerful muscles to cope with the constant downward pull. Tall creatures would collapse under their own weight. Evolution would favor compact, sturdy body plans with short limbs and reinforced skeletal structures. Perhaps beings there wouldn't have rigid bones at all, but flexible cartilage and dense muscle fiber networks, providing support without the brittle vulnerability of calcium-based skeletons. The thick atmosphere that likely envelops Kepler 452b would serve as natural armor blocking harmful cosmic radiation more effectively than Earth's thinner atmospheric layer. The light spectrum reaching the surface would shift toward red and orange wavelengths as the older star burns cooler than young suns. This spectral shift would fundamentally alter photosynthesis, making green plants an impossibility. Forests on Kepler 452b might be forests of darkness, vegetation colored purple, deep red, or even black, absorbing wavelengths that Earth's chlorophyll cannot use, extracting energy from light that would pass harmlessly through terrestrial leaves. Like looking into a mirror and seeing an older, wiser version of yourself. Staring back, Kepler 452b reflects what Earth might become given another 1.5 billion years of evolution and environmental adaptation. Surface temperatures estimated between 22 and 27 degrees Celsius place Kepler 452b firmly in the comfortable range, warm enough for liquid water, but cool enough to avoid runaway greenhouse effects. Yet the specter of Venus haunts every analysis. One miscalculation in atmospheric composition, one critical threshold crossed, and Kepler 452b could spiral into an irreversible greenhouse state, transforming from paradise to hell within geological eye blinks. Kepler 452b is why this story exists, why we build telescopes, why we dedicate resources to searching for exoplanets, because it represents the answer to our loneliness proof that Earth-like worlds orbiting sun-like stars are not unique accidents, but natural outcomes of planetary formation. But discovering these worlds raises questions far more troubling than any answer. How do we reach them? Across 1,400 light years of void. And if we somehow develop the technology to travel, there should we. Mars currently sits at the focal point of humanity's near-term exploration efforts, not because it represents the most habitable world we've discovered, but because it's close enough to reach with existing technology and harsh enough to serve as our first biological laboratory for testing whether life from Earth can survive, adapt, and eventually thrive in near-death environments. SpaceX's Starship program has fundamentally redefined what space travel means, shifting from the single-use, expendable model that dominated the 20th century to a fully reusable system capable of transporting dozens of people and hundreds of tons of supplies to the Martian surface. The stated goal sounds almost casual. In its ambition, establish a permanent base on Mars within the next decade, creating humanity's first foothold on another planet. But here's the uncomfortable truth that space agencies and private companies rarely emphasize in their promotional materials. We have the technology to leave Earth, but we lack the technology to ensure that future generations aboard these ships or living on Mars remain physically and mentally intact. The biggest challenge isn't rocket science anymore, isn't propulsion systems or landing mechanisms. It's radiation. Mars possesses no magnetic field comparable to Earth's protective shield, meaning anyone living there would face radiation levels many times higher than what we experience on our homeworld. Every day spent on the Martian surface or traveling through interplanetary space is a day of accumulated DNA damage, cellular destruction, significantly elevated cancer risk. Starship has powerful engines, but it doesn't have radiation shielding adequate for long-term human health during the months-long journey to Mars. We can get there. We just can't guarantee the people who arrive will be healthy enough to build the civilization we're promising. Meanwhile, our observational technology continues advancing at remarkable pace. The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will utilize advanced coronagraph technology to block out starlight and capture direct images of exoplanets, potentially revealing geographical features like oceans or continents on worlds thousands of light years away. This represents a monumental leap from detecting planets through indirect methods to actually seeing them as resolved objects. But even Roman's capabilities have limits. It can photograph planets, might identify large-scale surface features, could potentially detect seasonal changes in reflectivity. What it cannot do is definitively confirm biosignatures, the chemical proof of life. That requires the combined efforts of James Webb Roman and future generations of even more powerful observatories working together to build a comprehensive picture of distant worlds. The legal and ethical frameworks governing space exploration lag decades behind our technological capabilities. The 1967 Outer Space Treaty establishes that no nation can claim ownership of celestial bodies, a noble principle designed to prevent colonial conflicts from spreading beyond Earth. However, the treaty says nothing explicit about private entities exploiting resources from asteroids' moons or planets, creating a massive legal gray area that grows more problematic with each passing year. Private companies now possess the technology to potentially mine asteroids containing precious metals worth trillions of dollars or harvest water ice from the moon. Who owns these resources? Who has the right to extract and sell them? The treaty's silence on these questions threatens to create conflicts that could destabilize international cooperation in space. Then, there's the question that has haunted SETI researchers since the program's inception. Should we listen for signals from extraterrestrial civilizations, or should we send signals announcing our presence? Humanity asks, are we alone in the universe? While simultaneously worrying, but don't let anyone know we're here. Like having your ex's phone number saved in your contacts. You want to call, you're desperate to know if they'd answer, but you're terrified of what might happen if they actually do. Stephen Hawking, one of the most brilliant minds of our era, warned against revealing Earth's location to potential alien civilizations, viewing it as an existential risk. His reasoning was grimly pragmatic. Any civilization capable of receiving our signals and traveling to Earth would be technologically superior by definition, and history shows that when advanced civilizations meet primitive ones, the primitive civilization rarely benefits from the encounter. All this technology, all these ethical questions, all the promises and warnings and possibilities converge toward one final, inescapable conclusion about our place in the universe. This story began among distant worlds, planets so remote their light takes centuries or millennia to reach our telescopes. We explored hell planets, where glass rains sideways at supersonic speeds, ocean worlds buried beneath kilometers of ice, systems with 7 Earth-sized planets, orbiting dying red dwarf stars. We witnessed wonders and horrors, hope and devastation, the magnificent and the terrifying. But here's the truth that crystallizes only at journey's end. This story was never really about those distant worlds at all. It was always about home. The paradox revealed through exploring the universe is this: the more we learn about other planets, the more we appreciate Earth. Every horrifying exoplanet teaches us gratitude for what we have here, what we too often take for granted. Tari S2b, the planet that swallows light, teaches us to be grateful for sunlight warming our faces, for the simple miracle of photons traveling 93 million miles to illuminate our world without being consumed by darkness. Koro T7b, where rocks evaporate and rain back down as molten stone, teaches us to be grateful for cool air, for atmospheres that don't try to kill us, for the gentle hydrological cycle that brings life-giving water instead of death-bringing lava. HD 1899733b, with its supersonic winds carrying glass bullets through the atmosphere, teaches us gratitude for gentle breezes, for wind that rustles leaves instead of pulverizing everything in its path. Trappist 1 is fighting desperately to maintain its atmosphere against relentless stellar radiation, teaches us to appreciate our stable atmospheric shield, the delicate balance that neither strips away into space nor crushes us under impossible pressure. Kepler 452b, with its doubled gravity that would make every step an exhausting struggle, teaches us to be thankful for Earth's gentle 1G pull, strong enough to hold us but weak enough to let us stand tall. Earth is not the default condition of planets. It's a rare miracle, a statistical outlier, a cosmic accident so improbable we should be astonished it exists at all. 8 billion people currently live on the only blue jewel we know exists in the entire observable universe. We spend billions of dollars searching for water on Mars while simultaneously polluting the abundant water we have on Earth. The irony would be funny if it weren't so tragic, like traveling around the world, visiting dozens of countries, experiencing different cultures and landscapes, only to return home and realize your own backyard was beautiful. All along, humanity's exploration of the cosmos reveals that Earth is extraordinary, not in spite of being ordinary, but because it's actually not ordinary at all. The journey of space exploration reflects humanity's indomitable spirit, our refusal to accept limits, our compulsive need to push beyond every boundary. But it also teaches us about fragility, about how thin the line is between life and lifelessness, how delicate the balance that allows our existence. The greatest challenges we face, climate change, resource depletion, environmental destruction, can only be solved through cooperation and unity. Before we seek new homes among the stars, we must prove ourselves worthy of the home we already have. The question is not, is there life out there? The real question, the one that actually matters, is, do we deserve to exist on Earth? We need just one more breakthrough to know for certain we're not alone in the universe. But perhaps what we truly need is the wisdom to protect what we have before we lose it forever. The universe is vast, cruel, and magnificent. It contains billions of planets, ice worlds and lava worlds, diamond planets, and darkness incarnate wonders beyond imagination and horrors beyond comprehension. But there is only one Earth, and we are living on it right now, at this exact moment. Remember that.